All right, I will begin with a word of prayer. Heavenly Father, we thank you for your many blessings, and I just pray that you would be glorified in what we do, and that we all understand a little bit more about how to solve differential equations with a power series technique, Lord. In your name I pray, Lord Jesus. Amen. All right, so well, before I get into the new stuff, is there any questions about the old stuff? You guys are welcome to ask. If you got particular questions that's vexing you and you'd like me to talk about it, I can do that. We have time. But all right, so like the one I just gave you, one of those problems is genuinely different than anything we've done up to this point, in a sense, but in the same time, not really. So one of those is a system of differential equations, right? So like I think on the back side, there's a system. And so how do you solve a system of differential equations with Laplace transforms? You do exactly the same thing we did. You take the Laplace transform of both equations, all right? And then you're going to have a big X and a big Y. And then you're going to have to like do two equations, two unknowns kind of thing. You want to isolate, find just an equation in big X or just an equation in big Y, and then you can take the inverse transform of that, and then you'll have a solution. That's the technique, all right? I don't think there's even an example in my current notes on this, but there are, well, I do have an example written somewhere, maybe in like the old solved homeworks or something. I have covered it ages ago, but it's not any harder than what we've done. The thing that makes this interesting, of course, relative to the previous material is, well, there's a unit step function, right? So we're going to basically have a way to solve a discontinuous system of differential equations with Laplace transform. That's pretty much the point of that example. Oh, and I tried to come up with an example like the one I did last class using ChatGPT, and despite trying, like I just could not find my way to anything that was worth you guys trying. So I just said, all right, enough of that. We won't do that. So my apologies on that. That's just an isolated example in class. The one where I'm talking about the one where we took the Laplace transform and we ended up with a differential equation in the frequency domain, right? That's kind of an outlier in terms of examples. And I couldn't create another decent one of those for you guys. I'm sorry, I tried, but I just didn't. I spent like a half hour on it. I couldn't get it. So even with ChatGPT, it's still just giving me nothing pretty. So that's fine. I think all of those, I think an example which works out that way is kind of artificial, honestly. And then the other thing is I couldn't find a good periodic example either. I was like, there's a reason I don't cover Laplace transforms of periodic functions, and now I remember why. Because there's no interesting homework problems, at your level at least, all right? Like I think to do that, it requires some idea I don't have to make it interesting. So that's kind of also going to be, I mean, I might ask you to do something like we did in class, but that'd be probably about as far as it went. Actually, let me just simplify your life. I will not test the periodic function Laplace transform business on the test, all right? So you can rest easy about that. Okay, so let me go on then. I want to talk about, solving ODEs via series techniques. I can't spell. So, how do you think this is going to go? What do you think the method is? Trash. All right. Here's the method. Given an ODE, we propose the solution is a power series. That's the technique. And then you plug it in and work it out. That's the technique. So yeah, all right, so here's an example. So suppose we're solving y prime prime. Let's keep it simple to start with. Y prime plus y equals to e to the x squared. All right. We can't solve that by previous means because we cannot integrate e to the x squared, right? But if we want to find, so let's find a power series solution. Centered at 0, all right? And I'll do it two ways. Part A, just to order 3. And part B, the full complete solution, complete summation notation. All right? That's the problem. Okay, so the technique, the method is, that's not quite it. We propose power series, solution as a power series. Like the rest of the method that I haven't explained yet is everything in sight. Make it into power series. All right? That's basically the idea. You look at the differential equation and everything there, you want to convert it into a power series. So this one, we have, so first of all, our solution is like a0 plus a1x plus a2 x squared plus a3 x cubed, right? That's up to order 3. Now we don't know the coefficients yet. That's kind of the deal. It's like undetermined coefficients, except with infinitely many undetermined coefficients. All right, what's y prime? Well, that's a1 plus 2a2x plus 3a3 x squared and so forth. All right, so I go up here. I've got y prime prime. Y prime prime, what's wrong with me? Y prime plus y equals to e to the x squared. All right? So I've already kind of spilled the beans over here, how the left-hand side works out, right? My y prime is like, a1 plus 2a2x plus 3a3 x squared plus dot, 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 dot. And then my y is what? Well, a0 plus a1x plus a2x squared and so forth. I'm just going to go to quadratic. I'm only going to, okay, so here's the deal. I'm interested to order 3, right? But I'm pretty sure if I just look at the differential equation up to order 2, it's going to have all the information I need. So I'm going to stop at quadratic order in my expansions. So this is it. Up to quadratic order, that's the expansion, right, for my proposed solution. What's e to the x squared? What's its Maclaurin expansion? Well, this, right, is 1 plus x squared plus 1/2 x to the power 4, because it's x squared squared, and so forth, right? There I'm using the known Maclaurin expansion of the exponential. Those are the first 3 terms. I don't even need the first 3 terms. That's quartic, right? We don't care about that. So we'll just keep 1 plus x squared plus stuff I don't care about. All right? So then, what do? You have 2 series are equal. What does the theory of calculus tell you about power series? They're only equal if they're equal term by term, right? We can match coefficients. And so we do that. Like the constant term. I've got a1 plus a0 equals to 1. There we go. There's one equation. My next term, the x, I got a 2a2, right? And plus a1 equal to 0 apparently. All right. And how about x squared? X squared, I've got 3a3 plus a2 equal to 1. Now, this is a first order differential equation. How many constants should be in my general solution? Uh-oh. You guys know, right? First order differential equation. How many constants in the general solution? 2. You're saying that to be wrong, right? Okay. Good. So it's first order, so 1 constant, right? So which constant is the most natural one to use? What's the significance of the constants here? Do you guys remember how this relates to Taylor's theorem? It's the sum n equals 0 to infinity of like the nth derivative of y evaluated at 0 divided by n factorial times, x to the power n, right? So the significance of the coefficients here is like a0 is y of 0, right? a1 would be y prime of 0, et cetera, et cetera. Okay? Can you specify both y of 0 and y prime of 0 independently for a first order differential equation? No, you cannot, right? Only one data point for a first order differential equation can be given without stipulation. Okay, so my point is, the natural thing to do is to write everything in terms of a naught. I'm going to keep a naught in my solution. In view of that, this tells me that a1 is what? 1 minus a sub 0, right? There we go. I've got the first coefficient in terms of my my parameter for the solution. And this one tells me what? a2 is equal to minus a1 over 2, which is also known as a0 minus 1 divided by 2. See what I did there? I plugged the first equation into the second. Have you guys ever studied recurrence relations? Like difference equations? In like your discrete math course, perhaps? Nobody? You don't do that? What do they do in Math 250? Have you guys had Math 250?
Logic.
Yes, no, just logic?
Logic.
Just logic? Oh, man.
And like they teach you how to do proofs.
How to do proofs? Oh, no one needs proofs. Okay, I'm just kidding. Sorry. Yeah, my son is currently taking, just a second here. So 1 minus a2 divided by 3. Anyway, it's okay. We're going to learn how to solve these recurrence relations together. I mean, that's kind of the nature of the game here. But the method is simple enough. It's just regular algebra, but it's done in steps. All right. Okay, so we want to write our answer in terms of a sub 0. So my a sub 3 is actually equal to 1 minus parentheses a sub 0 minus 1 over 2, close parentheses, divided by 3. Which I guess we could clean up. What is that? That might be wrong. Yeah, that's wrong. It's 1/2. I think there's a net of a half there, right? Because the top gives you 3/2, but 3/3 over 3 is 1/2. But then you've got minus a sub 0 divided by 3, which is minus a sub 0 over 6. Es bueno? Muy bueno. All right, so here we go. Y is equal to a sub 0 plus a sub 1, which was 1 minus a sub 0 times x, plus a sub 2, which was apparently a sub 0 minus 1 over 2 times x squared, and then plus 1 half minus a sub 0 over 6 x cubed, and then plus dot 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 dot. Now I want to clean this answer up just a little bit to emphasize what's going on here, right? So we've got y is equal to a sub 0 times what? Well, times 1 minus x plus 1 half x squared plus 1 half x cubed if I haven't made a stupid mistake somewhere. Oops, minus 1/6 rather, right? Plus dot 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 dot, right? And then I've got, plus x minus x squared over 2 plus x cubed over 3. Oh, excuse me, over 2 rather. Plus higher order stuff, okay? The reason I wanted to write the answer like that is to emphasize what's going on. Can you guys recognize what's going on? Like, what's the significance of the terms? What do we call this piece? This piece over here. So this is y. Over here we've got y no homo, and over here we've got y homo. Genius. Okay, we usually call it y particular, but not the homogeneous part. That's what's coming from the e to the x squared term, right? If e to the x squared wasn't there, we'd just get the stuff with a naught. And we wouldn't have this pesky 1 and x squared term littering these recurrence relations with the constants. So another way to solve this that might have been cleaner would be to what? You could just like solve the homogeneous problem, right? And then solve the non-homogeneous problem separately and then add them together. I don't know if that'd be better, it'd be worse. It's something you could do. All right. So this particular example, I think there is a different way to do part B, which is like I'm going to do part B in a way which is atypical to other problems. Okay? I just want to illustrate the method, which is that you can use series to overcome obstacles that were in your way. Again, my method of calculation of what I'm about to do is somewhat atypical. But this problem we can solve the full thing using what? So this is a fine calculation. This is this is how we do things. All right. This is the method for like finding the first 3 terms. But if you want to find the whole thing, what is going on with this marker? Trash. How would you solve this kind of differential equation? What is it? This is a linear, right? It's a linear first order ODE. How do we solve those? What's our method? We'll start reviewing for the final now, right? Remember test 1? Remember calculus 2? Calculus 2, you should have seen this. This is the integrating factor method, right? The integrating factor method. What's the integrating factor here? I equal exponential the integral of 1 dx, so apparently just e to the x, right? So if I multiply this by e to the x, I've got e to the x times dy dx, right? Plus e to the x times y is equal to e to the x times, oh, it's ugly. Oh, it's hideous. Ooh, this is a nasty problem. Oh well, I maybe made this too hard. d dx of e to the x times y, right, is equal to Ew. E to the x squared plus x. Ooh. Ooh. Ah. Mmm. That's nasty. That's not nice. Oh, rats. I guess I can't solve this one in closed form. Phooey. Anyway, so the answer is e to the x y is equal to, of course, the integral of e to the x squared plus x dx, right? And so what we have then is y is equal to, e to the minus x times this integral. Which is not nice. It's really not nice. But you could do it. I mean, this is the integral of, okay, it's not too bad though. It's 1 plus x, x squared plus x, plus 1/2 x squared plus x squared plus dot 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 dot. I'm not going to be able to get the full series is the thing. I'm sorry, guys. I should bail on this example, really. So, all right. So I've got e to the minus x times the integral. So the constant term, there's just one of them, right? Like let's work this out here. So the 1 integrates to x, right? See that? This 1 gives you an x. What are the x terms here? What's the linear terms in the integral, in the integrand? Is there more than one of them? I don't think so. I think the lone linear term is right there. So that gives us a 1/2 x squared when we integrate term by term, yeah? Quadratic, there are 2 quadratic terms. Be careful. There's this guy, right? But this, when we square this out, it gives us, x squared, well, x to the 4th, right? Plus 2x cubed plus x squared, all times 1/2, right? And so we have a half and a 1, so we've got 3/2 x squared. So we get 3/2 x cubed over 3, right? And then, of course, plus a constant, which I'm going to write the constant at the front. Then we're not done, you see. It's really horrible. Because this e to the x is 1 minus x plus 1/2 x squared, you see. So I've got to take that and I've got to multiply it. I mean, this is a nice example in a certain sense, but it's also just really not the right thing to start with, so my apologies, but no, I regret nothing. All right, so 1/2. That's not true. Let's see here, but all right, so let me write this so you can see it. This red marker is just about invisible. So we know how to multiply series, right? How do you multiply series? What is a series? Well, a professor who used to work here, Dr. Kester, used to call them Texas-sized polynomials because he was from Texas, which I think may exaggerate the size of Texas slightly, actually, because power series are infinitely larger than polynomials, right? Okay, so look, but the way you multiply is just collect terms in like order, right? So there's a constant. There is minus cx. There is plus x. I think that's it for the linear terms. Then we get the quadratic order. We've got, what? I'll start with the 1. That gives us a 1/2 x squared. right? Let me show you my logic with some color coding. I'm doing this times that. That's this term. Next, I will do this times that. It will give me minus what? Yeah, minus x squared. Then we've got just one more, right? This one here. So we get plus, I've lost the plot, c plus c over 2 x squared. That's it to quadratic order, right? So group everything together here. We've got the constant times 1 minus x plus 1/2 x squared plus dot 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 dot, right? And then what else do we got? We've got plus what? Without the constant, I've got x and then minus 1/2 x squared, I think, and then higher order stuff. Now, I'm afraid to look at my previous answer and compare. Well, look, my constant is the significance of the constant is that it's the a sub naught, right? You can compare a sub naught is like the constant. Here I've got 1 minus x plus 1/2 x squared. Here I've got 1 minus x plus 1/2 x squared, right? And the no homo term, I've got x minus x squared over 2. Check it out, yo, right? Which is a better method? I think that way is better. This way, in some sense, is safer because you don't have to like solve the equations, right? There's a certain thing I did in the previous one. Like if you hadn't seen through these equations, you'd have been stuck here, right? But this is a method that you might, if you trust in yourself to be able to do calculations with power series, this would be a natural thing to try, right? But it's still hideous. All right, let's try another example that's prettier. All right. Let us work out. Oh no. Well, I don't know how this is going to go, guys, because I don't have the juice today. So this board is kind of trashy. Well, all right. I think we're going to be okay. All right. Next example. Let's solve y prime prime minus y equals to 0. Now, okay, so like part of me like doesn't want to do this because we already have a method, right? Like we don't need to do what I'm doing. But I think it's helpful for you to see an easier example worked out so we don't get lost in the sea of madness, like example 1. So let's work a slightly easier example. All right. So here we go. Y is equal to the sum n equals 0 to infinity of a sub n x to the power n. I'm looking for the series solution centered at 0, okay? Trying to find the power series solution. Find power series solution centered at x equal to 0. All right. So first order of business, there you go. There's my series. Second thing, oh man, this board is substandard, to put it lightly. Okay, so y prime is what? It's the sum n equals 1 to infinity of n a sub n x to the n minus 1. This is term by term differentiation. Do you see why we start at 1? right? Because the other is 0, yeah, it's 0. Now y prime prime is the sum n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. All right? Now, I'm going to do a little switcheroo here. This is equal to the sum j equals 0 to infinity of a sub j x to the power j. Because I can change the letter n to the letter j, and it doesn't change the substance of the summation, right? It's a dummy variable of summation. Now, I'm going to do a less dumb thing down here. I'm going to let j equals to n minus 2. If I do that, n equals to 2 gives me what? J equals to what? J equals to 0, right? And also n is equal to what? J plus 2, right? So in terms of that, those rules of engagement here, this is the sum j equals 0 to infinity, all right? N is j plus 2. All right? And n minus 1 is what? J plus 1. All right. A sub n is a sub j plus 2. And then, of course, we have x to the power j. Now, the reason I've done this is so that when I substitute it into the differential equation, I can combine the summations. The only way you can combine two sums is if they have matching monomials. Like I have to have the same power structure. I have to have x to the power j on both of them, otherwise I can't combine the sums. But if I have, like this is just a theorem, right? If I have the sum over like c sub k x to the k plus the sum over d sub k x to the k, and it's the same, you know, k equals 7 to infinity, whatever, right? Well, that's the sum k equals 7 to infinity of parentheses c sub k plus d sub k times x to the power k. Like that's a theorem of power series. We can add matching sums. Yeah.
So then why didn't we just keep it in the n? Like in terms n, why did we have to?
Because this and this
We're not the same.
do not match. Right. Yeah.
So would we be able to substitute if the n's were still the same, but like we started at n equals 2 and n equals 0, would we have to change the bounds then?
What if they don't have the same starting point?
Yeah.
What do you do then? Then you have to split off whatever is exceptional. And that will be an issue. Yeah. Okay, so what we have then is, let's work it out then. We got y prime prime minus y equals to 0, right? Which, in view of the summation, in view of the formulas I have on the board, is the sum j equals 0 to infinity of, well, my y prime prime is j plus 2 times j plus 1 times a sub j plus 2, right? And then I have to subtract a sub j, and then I've got my x to the power j, and that's all equal to 0, right? Do you guys follow what I did? Or do I need to write more? I could write more. Like the step I've not written essentially is the theorem at the top, right? It's like this times x sub j minus that times x sub j, so I can put it together. In words, the difference of two series is simply formed by the series, the summation of their differences, provided that the monomial, the x to the whatever, is matching. I have to have matching monomial x to the whatever. I have, all right, so how can this be true? How many equations is that? Talk to your friends later, you're like, in differential equations today, we solved infinitely many equations. Because that's what we're doing at the moment. That's infinitely many equations. Like every single choice of j is a separate equation. We get that j plus 2 times j plus 1 times a sub j plus 2 minus a sub j has to be equal to 0 for all j. I don't know about you, but I'm tired of writing j. I'm going to switch back to n because it's easier for me to write. Okay? So pick the letter you're most comfortable with to do most of the calculations, all right? So this is, in other words, n plus 2 times n plus 1 times a sub n plus 2 equals to a sub n for all n. But perhaps it's better to look at this as a sub n plus 2 is equal to a sub n divided by n plus 2 times n plus 1. Now, maybe you don't like that. I look at that, I'm like, I don't really like that much. I don't like the pattern. I think I want a formula that looks like this. It's a sub n is equal to a sub n minus 2 divided by what? N times n minus 1 is the pattern. Correct. Because this matches. And then it's one less. So get comfortable. Find the nicest form of this equation that you can. And then go to town on it. Like try to figure out what does it say.
Does the upside down A mean for all?
Oh yeah, that means for all. Yes. Yes. Sorry, forgot where I was. Hey, wait a minute. You guys should have seen the for all symbol. At some point, your calculus professor should have, succumbed to their more base desires and written the for all or there exists somewhere. Surely it happened. But yeah, that just means for all. For every upside down A, there's a backwards E. Let's see here. Something people say. Okay, so look, let me, I'll write it up here just again for good measure. We are bound by this recurrence relation. A sub n is equal to a sub n minus 1. Minus 1, no. Minus 2 times n minus 1. All right, great. So at this point, let's consider n equals to like 2k, right? So a sub 2 is equal to what? A sub 0 over 2 times 1. This was k equals to 1, okay? K equals to 2, what do we got? A sub 4. It's always 2 less, right? So a sub 2 over 4 times 3. But that is actually a sub 0 over 4 times 3 times 2. And you can throw a 1 in there if it makes you feel better. Sometimes that makes me feel better. How about k equals to 3? We have a sub 6 is a sub 4 over 6 times 5, which, by the way, is a sub 0 over 6 times 5 times 4 times 3 times 2 times 1. Do we see the pattern? Or do I need to do more? You guys tell me the pattern. A sub 2k is equal to a sub 0 over what? 2k factorial. Yeah, 2k factorial. Meh? Meh, 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 meh. Now, what's the other possibility is you could look at odd coefficients, right? So listen, I know as I look at this that odds are linked to odds and evens are linked to evens because of the recurrence relation links every two. Part of what made example 1 so hideous is that it wasn't like that. It was all intermixed. It was all intertwangled. So if we could look at n equals to, like, say, 2k plus 1, right? If I look at k equals to 1, that gets me a sub 3 is equal to a sub 1 over 3 times 2. And then k equals to 2 gives me a sub 5 is equal to, a sub 3 over 5 times 4, which is a sub 1 over 5 times 4 times 3 times 2, right? K equals to 3, a sub 7 is a sub 5 over 7 times 6, which is a sub 1. Oh, man! All of a sudden. Whoa. You guys did this to me. All right. It's not your fault. 7 times 6 times 5 times 4 times 3 times 2 times 1. There, times 1. Times 1. Anyway, the point is, you can see the pattern. What is it? A sub 2k plus 1 is apparently equal to a sub 1 divided by 2k plus 1 factorial. All right. So let's go back to the beginning. We started with our solution having the form y equals to the sum n equals 0 to infinity, right, of a to the a sub n x to the power n. Now I can rewrite that as the sum k equals 0 to infinity of a sub 2k times x to the power 2k plus the sum k equals 0 to infinity of a sub 2k plus 1 x to the 2k plus 1. Now why can I do that? What's that step? It's just a purely combinatorial step. It's just common sense. All I'm saying is that if you think about the totality of non-negative integers, you can divide those into the evens and to the odds, right? And that's what we want to do here because the pattern breaks into the even and odd cases. And so then I can put in my formulas for a sub 2k and a sub k, and what I got then is I've got y, and I'll pull the constant out if you guys don't mind, a sub 0 times the sum k equals 0 to infinity of 1 over 2k factorial x to the 2k, parentheses, plus a sub 1, parentheses, sum k equals 0 to infinity of 1 over 2k plus 1 x to the odd power x to the 2k plus 1. That's the general solution. We expect there are two constants here because this is a second order differential equation. So of course it must have two solutions. Two linearly independent fundamental solutions. They're both homogeneous solutions. So this right here and this right here have names. Name names, right? What are their names? What's that?
I made a joke. I said Heisenberg.
Oh, Heisenberg. That's Heisenberg, and this is Noether, or maybe no. Nobody? You guys need a refund from calculus too. You should totally do a refund. These are Taylor expansions of known elementary functions, yes. All right, now this is the hyperbolic cosine. This is cosh of x, and this is sinh, right? What's the difference between sine, cosine, and cosh and sinh? Is sine and cosine have a plus minus in their expansion, right? this derivation we just did, if you go back to the start and you put a minus, you change that minus to a plus, all right? That will end up making these recurrence relations that we have on the board flip back and forth, plus minus, plus minus, plus minus. What happens is you end up with like a minus 1 to the k here and a minus 1 to the k here, and you get cosine and sine as solutions. So, in fact, this is a way of defining sine and cosine. You can say, well, sine and cosine are simply the homogeneous solutions to the differential equation y prime prime plus y equal to 0. That's like a legit way of defining sine and cosine, completely independent of geometry. Right? You can say cosine is the solution of y prime prime plus y equal to 0 such that y of 0 is 0. Excuse me, y of 0 is 1 and y prime of 0 is 0. And then you can say, well, sine is the solution of y prime prime plus y equal to 0 such that y of 0 is 0 and y prime of 0 is 1. And that would uniquely and completely define sine and cosine in terms of, well, apparently they're Maclaurin expansions. In the same way, we can define cosh and sinh as the, likewise, solution to the initial value problem for y prime prime minus y equal to 0. This one has y of 0 equal to 1, y prime of 0 equal to 0. This one has y of 0 equal to 0, y prime of 0 equal to 1. Derivative of cosh is sinh, derivative of sinh is cosh. Anyway. Now, if this problem comes up on the final, unless I, put handcuffs around the problem statement and say, solve this by power series, I highly recommend you don't solve this way, right? Because we already know this solution through other means, right? So, like our usual song and dance would have been what? Y prime prime minus y equals to 0. We write down lambda squared minus 1 equal to 0. Therefore, lambda is plus or minus 1. So y is equal to c1 e to the x plus c2 e to the minus x, right? And then that can be rewritten as this by an appropriate redefinition of constants. E to the x is cosh plus sinh, e to the minus x is cosh minus sinh. So they're kind of the same universe of functions, but anyway, that's all I got for you guys today. So next, well, I forget if I put this class down for CFA or not. The CFA may be did they come last time? I can't remember.